Good afternoon. This is the second lecture on non-pipeline processors, and last time what we designed was a single cycle processor, but for various reasons, as we learned today, a processor can't execute every instruction in one cycle. So we will examine the reasons why a processor can't execute every instruction in one cycle, and then see what happens when it can't. Then obviously an instruction is going to take multiple cycles to execute. And it's interesting because not all instructions will take the same number of cycles, or how to deal with these issues. And another very high level idea that you have to remember is the moment an instruction can't execute in one cycle, then you have to remember some data from one cycle to the next to continue the execution of the instruction. Okay, so that's what we'll be focusing on, multi-cycle processors. So let's begin with where we were last time. We saw the single cycle RISC processor where the register file allowed 2 reads and a write, which is essential if you want to do it in a single cycle, because many instructions read 2 values and write the 3rd value back into the register. And another important aspect of it was that it had separate instruction in data memory. Whenever a computer has separate instruction in data memory, it's referred to as Harvard architecture. I won't go into the obscure reasons why we call them Harvard architectures, but in the beginning of computers, instructions were regarded as something very, very different from data, right? And in fact, different technologies were used for storing instructions and data. But if you there are many things we can talk about, and we'll see what happens if we put them in the same memory, both instruction and data. Now, another thing I want you to get used to it, I show these pictures with data paths drawn, how these boxes are connected. They're only suggestive. They're only to give you more intuition about what's happening. They are not very accurate. Okay, so if we start looking at the details of it, maybe there should be some line here and there, but we try to capture all the important aspects. The real data path, how these boxes are actually connected, is always generated by the compiler. So you write your BlueSpec program, and that dictates how the things will be connected. So it's never the case that you have a picture in your mind and then you try to code it. It's the other way around. You have some idea of how this computer should be organized, you write code for it, and that generates the accurate data path. So these pictures are suggestive as opposed to prescriptive in what we're going to be doing. And all throughout this course, we are using the RISC-V instruction set, and we already finished building one last time, and today we'll refine it more. We'll see this simple RISC processor, how it can be made more realistic. Okay, so just let's quickly go over what we saw last time, that in this single cycle implementation, we have this module called make processor, and its interface is empty, and I'll come back to it towards the end of this lecture, why the interface is empty. But at high level, it means it has no methods visible to the outside world. And we, as usual, start out by enumerating what state elements do we need. And it's pretty obvious in this simpler processor. You need a program counter, you need a register file, and you need an instruction memory and a data memory. That's what is written over here. These are instantiations of the state. Whenever you instantiate, you see this left arrow, syntax-wise. Okay, and then in this simpler processor, there is only one rule, which we have just named do processor, right? You have to give it some name. So what is the very first thing I do? I fetch the instruction from the memory. All right, so I'll get 32 bits back from the memory, and now I have to figure out exactly what do these 32 bits mean, right? That's a very important part of the lab you're doing currently, where you have to decode it. You have to figure out what these 32 things do. And decoding essentially means that there are some fields in this instruction which I have to know before I can execute it. I have to know where are the register sources, where is the register destination, what is the opcode, etc., etc., etc. So this is what we call a decoded instruction. And fortunately for us, RISC processors in general, RISC-V in particular, have an extraordinarily simple decoder. Right? If you go back to the old-fashioned instruction sets, then the decoder itself used to be a very, very difficult thing to design. That's no longer the case. I mean, you know, if you had told somebody 50 years ago that decoder will be given as a one lab exercise in an introductory course, people would have been shocked, right, that you can do that. All right. So it extracts these fields. That's the job of the decoder. Now, once we have decoded the instruction, we always need to find out what is the value in the registers, right? So there's the register file, and the instruction specifies the sources, source 1, source 2. Not all of them have both the sources, but let's just assume for a moment they do. So we go and read these values from the register file. Why? Because dinst.source1 tells me what is the name of that register, what is the number of that register. And once I know that, then I can read it from the register file module. Okay, now after I know all the fields and I have read the data, I am essentially ready to execute the instruction. And this may come as a little bit of a surprise to you. We deliberately separate the idea of what new values are needed when we execute this instruction, what values will be created, and we separate this act from actually storing them to update the state. All right, so we have to figure out, so for example, if the instruction says add, all right, so I have to figure out what is the value after addition. But then the act of actually storing it in the register file and actually updating the program counter, etc., we treat it as a separate act. And the reason for that will become clear to you as the course progresses. Anytime you commit a change in the state, it's all over. You know, there is no going back. Right? So we try to be very careful about state commitments. So first we will say execute instruction should produce the following values which will be used to commit, and that will be used to update the state of the processor. So all the meat in this is in the execute function, you know, which is telling you how to compute these values, and you saw it last time. Okay, and now again, I have just returned an executed instruction. einst is the output of the execute function, but einst itself is a record. So there are many, many fields in it, what type of instruction it is, you know, whether it has a destination in which to write the data, and what is the data to be written in case it's a memory instruction, what is the address to be done, and what is the next value of the program counter. Because next value of the program counter is not simply PC plus 4. It depends on what instruction it was. Whether it was a jump instruction, whether it was conditional jump instruction. So if it's taken, it's something else, otherwise it's PC plus 4. So there is a lot of stuff that execute has to do. It computes the value needed to update the processor state. And finally, we can take all these things and put them in a function called update state. And this is kind of cute, you know, I could have written out all the code, you know, but you can also write it as a function. So it's not a big deal, you know, if you don't like these functions, you can write out the whole code, but really this is legal code here. So I'm just calling it a function, update state, which given all these values will go and update the state of the processor. Okay, actions to update the processor state. So notice in this, nothing else is an action. Until now you're just reading the instruction, decoding it, reading the register file, reading, you know, doing the execution, but it's only this function that actually goes and updates the state of the memory. Okay, so this is the most important thing. Okay, so now let's just remind ourselves of hardware intuition, and we will do this in this course periodically. In fact, almost in every lecture, because we start writing code at such high level that if you're not careful, you'll lose track of what hardware is being generated. You'll just start looking at it as a program. But remember, this is the essential part of this course. Blue spec programs represent hardware. They're not there just to produce an address. They're there because we are trying to generate hardware. We are always determining the quality of hardware to be generated, how much area it takes, how fast I can run my clock on this stuff, right? So let's just get a feel for what's going on here. So you have a register file, given two sources, you get two values out of it. These are combinational reads, from the register file. Where do these sources come from? We have a decoded instruction which has many, many fields, and two of the fields in that are source 1 and source 2. The other refrain is any time you see some module, some method, some function being reused from being used in two different places, then there has to be a mux that goes with it. Right? So there has to be, you have this ALU where we'll be feeding this, and you have the immediate, sometimes you use the immediate value coming out of the instruction, and sometimes you use the value you read from the register. So we don't write down these muxes in our code explicitly, but they will always be generated. Right? So if you are writing into anything from two different places, it's certain that there is a mux somewhere, which will choose the right one to be going into it. Now there is one more thing to be noticed about this register file, that what happens if I read it and the register file field itself was invalid. Right? I mean, had no source 2, for example, an instruction. What will happen? These are combinational reads. It doesn't matter what you read. Right? So you can take any 5 bits and any address you want and read it. We'll just be very careful in our use that we never use a value when the register source itself is undefined in the instruction. But in terms of hardware, just reading it every time, there is no cost to it. You can just always do that. Okay. So this is a fairly important idea. Let's look at it. So remember, whenever we do execution, we are always looking at the type of the instruction and doing something. And you will notice that there are several instructions that call ALU. So for example, if it's either op or op immediate class of instructions, they're going to invoke the ALU from it, right? So that's why you have two uses of ALU. So the question is, how many ALU circuits should be generated? Now these two ALU operations are not happening in parallel. I mean, either your instruction is of type op or it's of type op immediate. So you would imagine that if the compiler is smart, and if we want, we can share that ALU from it. And there is a good chance that Blue Spec compiler will share that ALU. It will use just one ALU and put the values. Otherwise, it will have to go and duplicate the ALU circuit. But in fact, these things are a little bit difficult to be sure of, because anytime you say, well, if the compiler is optimizing kind, it does this. If it's not, it does that. So whenever you get into that thing, we have to move the correctness issue somewhere else. Correctness issue here is it doesn't matter whether it's duplicated or not. You'll get the right answer because ALU is a pure combinational circuit. You give it the same input, it'll produce the same output. So it's perfectly fine to have two different ALUs, but for various reasons we may want just one, to save the area. But the question about saving the area is not so obvious because muxes take a lot of space too, right? So, but anyway, and the only way you can be sure about what happened here is you'll have to go and examine the output circuit that is generated. And for that, there will be tools to do that. Okay, but I want to raise a slightly more subtle issue. Now, what about this add operation, val1 plus immediate? This is the address calculation going on. Could it have used the same ALU? Could it have used the same ALU? So if instruction is op, use ALU. If the instruction is op immediate, use ALU. If the instruction is load, perform an addition, could have I used the same ALU to perform that addition? Yes, because it's again mutually exclusive. Either an instruction is op immediate, or it's load, or it is store. So if we really want, we could have set it up so that even this thing will use ALU instead of writing val1 plus immediate. I could have written ALU and given these as parameters to it. Opcode would have been plus in that case, and see what the system does with that. All right, so this is something to think about. Should we share the same ALU or not share the same ALU for doing this address calculation? Now, what is important to notice here is reuse is not necessarily a good idea. Why are we doing reuse in circuits? Anyone? Why would you want to use the ALU over and over again? Yep.
To save space.
To save space, to save area, right? If the same circuit can be used. So if for whatever reason that condition is not met, then it's not a good idea to share, right? So why that condition may not be met? Well, look at PC plus 4. Well, that's an addition too. But now you know enough about combinational circuits that if I gave you as a problem to design me an adder that only adds 4 to something, right? That'll take a lot fewer gates than an arbitrary adder that can add 2 values. So this is where the problem comes in. When you share, you discourage specialization of circuits. And specialization, as you will learn more and more, saves a lot. Your circuits can become much, much smaller. If you know what is the other value to be added, right? Lots of automatic optimizations will set in. So I'm giving you a very confusing message here. I'm saying, yeah, we can share it, ALU will be shared. Then I'm saying, well, maybe it won't be shared. Maybe I don't want it to be shared. Basically, I'm letting you off the hook. In this class, we generally do not concern ourselves with sharing of combinational circuits because it is so difficult to fight with the tools. You would not know whether how to write your code so that the circuit will be shared or circuit will not be shared, because compiler has its own ideas, backend tools have their own ideas of how your code should be optimized, right? So whenever it comes to combinational optimizations, we worry about certain optimizations, but sharing is, leave it to the tools, right? Let them decide whether to share or not to share. I won't say that about modules. So when it comes to module sharing, there'll be more concrete examples of why you don't want to share modules, and you should have explicit control over whether you have 1 or 2 or more modules of the same type. All right, so what is the Princeton architecture? The Princeton architecture is we can take this Harvard architecture, but we want to store them in the same memory. So we bring these memories together. Why? Because one of the biggest advances in computing, without that we couldn't have gotten off ground, was the fact that you can do arithmetic on instructions the same way as you operate on data. This was so important. Without that, in the beginning, people could not have written any codes on the first generation machines that were built in 40s and early 50s. So at that time, when somebody said, oh, you can do arithmetic on the instruction itself, people said, that's cool, right? And that opened up so many possibilities. But at the same time, it's very deadly. I mean, when you do arithmetic on instructions. So, ever since the thing was discovered, we have spent the last 60, 70 years trying to come up with techniques so that you don't have to modify the instruction, right? We don't like self-modifying code in general. But at the architecture level, if you put them in the same memory, then you will have what is called a Princeton architecture, because this idea was attributed to von Neumann, who was at Princeton at that time. So Harvard people, 2 separate memories, Princeton people in the same memory. All modern computers do it in 2 different memories, and we worry in the background how we can make them the same, how we can keep them coherent with each other. All right, so memory instructions. So what I'm interested in this lecture is what is the consequence? Suppose I said, instead of having two memories, I have only one memory. What will it do to my design? Should I stand up and say, sorry, now I can't design my computer? No, the answer is of course we can design a computer. It's just that we can't execute instructions in one cycle anymore, especially a memory instruction, because in the same cycle you want to go and fetch the instruction and then you want to perform some data operation on the memory. And if you have only one memory, these two operations cannot be done in the same cycle. So we can't do instructions fetch and load store at the same time because there is only one memory. Now, whenever you see this kind of a situation, that conceptually these things could happen, but they cannot happen concurrently because of lack of resources, because we happen to put them in the same memory. Such condition is known as structural hazard, right? You have created a hazard just because you don't have enough resources. And as the name implies, anytime you have a structural hazard, it's always possible to solve the structural hazard by providing more resources. So structural hazards are important to understand, but they are not fundamental, because one solution to structural hazards is just have more resources, right? Duplicate the memory. Okay, extra. And so what that means is an instruction is not going to execute in one cycle. So I execute the first cycle of the instruction and now have some temporary information which I have to remember until the next cycle when I finish the execution of the instruction. So these two ideas go hand in hand. The moment an instruction is going to be multi-cycle, there is going to be some registers yet to be defined, right, which will hold the temporary information that you have generated in cycle 1 to be used in cycle 2. Okay, so this is the picture I have drawn here for you, where both instruction fetches and data accesses come to the same magic memory. So that's why I put a mux. Remember, whenever something is accessed from two places, you have to have a mux in it, right? Now every instruction is going to execute in two cycles. What will we do in the first cycle? We will just fetch it, right? So remember, if I have fetched it and I have to remember the instruction until the next cycle, I have to have a register. So let's introduce a register. I will call it fetch to decode register. So the instruction that comes back from the memory, I put it in the fetch to decode register. Now I'm ready to go to the next cycle. And what do I do in the next cycle? I will go and execute the instruction in the whatever is sitting in F to D register. How do I know whether I am in the fetch stage or whether I'm in the execute stage? So I need another register. I need a single bit which tells me I'm in the fetch stage, I'm in the execute stage. So after fetch stage, I'll put it back into the execute stage. After execute stage, I'll put it back into the fetch state. Is this point clear to everyone? Right? Two cycles. First one is being called fetch. The next one is being called execute. Right? And your instruction will come, start in the fetch stage, go to the execute stage, done. Then we go to the fetch stage again for the next instruction and execute it and so on. So that's the kind of machine we want to build now. And actually you have already done most of the work. So now if you have the first one working, designing this two-cycle processor is really quite straightforward. So what you do in this case is I have declared these two registers now, F to D, because remember, any state you use, you have to instantiate it explicitly. Okay, so you have to have this make register F to D, and it'll hold word or whatever you need to remember from one state to the next state. Then you have a state element, and it'll have two rules. First rule has a guard which says state equals fetch, and the next rule has a guard which says state equals execute. So they are mutually exclusive rules, right? Either you're doing the fetch or you're doing the execute. All right, so what does the first rule do? First rule, if the state is fetch, then fetch the instruction and put it in F to D. And don't forget, and change the state to execute. Trivial to do, right? This is how you'll do it, right? You just take F to D, the instruction you got from the memory. How you got it from the memory, that's exactly the same code as you saw before. And now you flip the state. You say next state is execute. Is everybody with me on this? Straightforward, right? And in the next rule, what are we going to do? If the state is execute, where is the instruction sitting? In F to D, right? In F to D registers. So I can take and look at the various fields in the instruction, you know, and invoke the execute function. Go to decode the instruction in F to D, execute, update, etc. And after, this is the same code, that's why I'm not writing. That's the code in green that you have already seen. And all I do at the end of it is say go back to the execute stage. Do you follow the whole idea behind two-cycle processor? The first cycle just read the instruction, put it in F to D. Second cycle, we executed the instruction as before, except that instruction came from F to D and not from memory directly to us. Okay, so it's going like this, right? Cycle 1, cycle 2, cycle 1, cycle 2. So every instruction now is going to take, you know, twice as long to do, but it's possible that the cycle time will be smaller. We'll discuss that later. All right, so now let's examine. I want to improve on this. And this is what we'll do all the time. We start out with the design, I can do better, right? So let's see how we can do better. So I look at the execute part of the pipeline here, right? So we have instruction, we are doing the decoding of it, etc., etc. And in the execute part, notice what all do we do? What all do we have to do in the state update part? We have to access the memory, right? If it's a store instruction, you'll go and update it. If it's a load instruction, you'll go and initiate, you'll read it from the memory. And then you have already got the value from the execute, so you will go and now do the execution. Sorry, you will store the value in the register file, right? So that's what this code is here. Very hard for me to point to, where is it? This one, right? So if you had a valid destination, then you're saying update the register file. And the last thing is whatever PC you had got from einst, you're going to update the PC accordingly. And notice this, the next state is fetch. This is already what we have discussed. Why am I showing you this code? When do you actually execute this memory part of this execute rule? When is this code executed? Is this code executed by every instruction? This is not a tricky question.
No.
This is executed by? Only load and store instructions. You say, oh, okay, let's think about this for a second. We went to 2 cycles because we says, oh, because of the memory instructions, I may be accessing memory and I can't access memory while fetch is going on. What do we discover in execute? Only load and store instructions access memory. Others don't. Well, we could do better then, right? We could execute all instructions in one cycle except load and store instructions. We can execute all instructions in rule 1 itself. But if it's a load or store instruction, we say, wait, you know, we have to, it's going to take some time, because I have to use the memory again, and this fetch rule uses the memory. So how do I organize that part? So now what I'm trying to do is improve on the design we had. The design we had, every instruction took 2 cycles, but it stands to reason that at least all the non-memory access instructions we should be able to execute in 1 cycle as we used to. So let's see how we can do that. How to do that, that's the question. All right. So fetch and decode execute in 1 cycle for all non-memory instructions. So I don't need this F2D register, right? Because I'm just going to take it out, execute it right there. But I have to have a test. If it's a load and store instructions, then I can't execute it. And in load and store instruction, I will have to save the partially executed instruction state in some register. So I'll have to introduce another register, from here, it'll go here, right? I take out the F2D register and I put a register here. But most of the time, we don't store anything in that register. We will be writing into that register conditionally. We'll be writing into that register only if it turns out that the instruction you want to execute is a load or store instruction. All right, so let's see what the code will look like for doing this. In the next cycle, we'll do the memory operation on this. Data paths for EM is not accurate. I mean, this is what I have to always remind you, that these pictures are just to help us understand conceptually what's going on. All right. So yeah, by the way, this is what Lab 6 is about, right? So this is Lab 6. All through these last lecture and this lecture, I'm giving you pointers to what problems you are solving in Lab 6. All right. So now let's look at how will the code be changed for this. So we had this do fetch rule, and in this case we were fetching from the instruction, etc., from the register file. We are executing the instruction, and we'll be done unless it's a load or store instruction. So therefore, I put a check here. If it's a load or store instruction, then what do? Then whatever information I have gotten so far, I put it in this register called E to M, execute to memory. And the rest of the stuff, oh, by the way, yeah, if I put something in E to M, that means I have to go to another state, which I'm calling the memory wait cycle or memory access cycle in this thing. If it is not a load or store, then what do? Then I'm back to the normal case. Just update the register file and do the rest, right? Then go and say next state is not the second cycle, but the same cycle. Go back to the fetch stage again. I hope everybody understands what's happening. So we have this as the primary rule here. And it executes instructions in 1 cycle, unless the instruction happens to be a load or a store. If it's a load or a store, then I store the partially executed instruction in some register, which I'm calling, I think, E to M. And at the same time, I am saying, okay, the next state is not fetch. The next state is memory access. I've just named it memory access state. Okay. So save the executed instruction state in E to M register. And this is what your the second rule looks like in this case. So if you have a memory access, if the state is memory access, so again these 2 rules are mutually exclusive. Either you are in the fetch stage or you are in the memory access stage, right? If you are in the memory access stage, then you will go and update the register file again, as we used to, and state becomes fetch. Go back to the fetch execute stage. I think I'm goofing up with names here. I have called the rule do fetch. It should be called probably, no, state name is fetch execute. That's fine. How many people have gotten the high level idea here of what's going on? Very good, very good. So I think it's really, the thing is, we have gone from a system where every instruction went 1, 2, 1, 2, 1, 2. Now we have gone to a system where most instructions are 1, 1, 1, but once in a while we get load stored, we get 2, right? And then we come back to 1 again after we do that part. These are variable number of cycles per instruction. Why are we going to this complexity? Of course it's going to take fewer cycles when you do this than every instruction taking 2 cycles. Okay, so this is good news. All right, performance implications, I already explained it to you. So suppose fraction f of the instructions n you executed happen to be load store instructions. So then what will happen? You can do this simple arithmetic that the time it will take, because fraction f of the instructions, fraction f is the non-memories. No, fraction f is the memory instructions, right? So fraction f is the memory instructions. They are all going to take 2 cycles, and 1 minus f, the remaining instructions, are not memory instructions. They're just going to take 1 cycle. So you can see what happened. Instead of having 2 n cycles, we now have only 1 plus f n cycles. This will be a significant improvement if you believe that memory instructions are probably not going to exceed 25% of the total instruction count in your program. Big win, right? Over 2n versus 1.25n. However, cycle counts is not the full story, right? If you're talking of performance, then we always have to worry about what will happen to the clock cycle. Because if the clock cycle gets longer, then you're not winning. So we always have to pay attention to that. We'll come back to this later. Now I come to the most important part of today's lecture, because from now on we will never look at magic memory again. We're just going forward. So every design we do will deal with realistic memory. And the interface of realistic memory is simply the following. There are no combinational reads. You submit a request, and maybe in the next cycle, maybe who knows how many cycles later, you will get an answer. So it becomes request response kind of a unit, right? You're familiar with request response kind of a unit when you design, for example, GCD, right? You have designed many modules already where you initiate something, it takes indeterminate number of cycles, and then an answer comes back and you say get ready, right? When it's get ready, then you go and get result, sorry. Whenever it's ready, you get it. Same idea in memory. So we will enqueue our request in the memory and we'll pick up the result whenever it's ready, and guards will take care of all such things. So this is what the interface will look like into the memory. Right, you as usual have enable and guards, etc. in forms of these ready signals. Okay, no response for stores. This is another thing which is true about realistic memories, that when you do a store, you just launch it. You say, please store it. You don't get a response back saying, I'm done storing. Because as you will learn more about architecture, it's a very tough question to answer. Store has been done, right? We don't know what the hell that means, store has been done. Only way we can tell is if the subsequent loads do the right thing, right? So we try to avoid asking the question, a store has been done, because that's not a very well understood concept at a high level. All right, so we'll just assume our memory doesn't return any signal saying the store has been performed. So this is the interface for this memory. It has the method action, method request, and it has an action value method, which is the response to it. Okay, so because any time you're doing a store, and we have to, because we have only one port, even the loads have to be treated the same way. You know, you're putting something into the memory from which you will get a response back. So the important thing to understand here is what is the structure of a request. So memory has only one port, right? All the reads and writes go through the same port. So the data you feed to it, the thing you feed to it has to have an opcode in it, which will be either load or a store. Anytime it's a memory operation, you have to have an address with it. And if it's a store operation, it also has to have a data in it. If it's a load operation, then data field is meaningless here, but it will return the data, from that, which we can check through this. So this is how you will see it. If you have a load request, notice I have put down there so this data is bogus here. So this is the default word value or something, right? But here, when we are doing the store operation, then I have to supply an address as well as I have to supply a value. And now how do I get the load response from it? I have to write some code like this. Let data get from M request, M response. So you'll be getting it's an action value thing. You're picking some value up from the memory. What that tells you is when you do a read from the memory, that value actually is not dequeued. That value doesn't disappear from the memory unless you take it. Right? So you can take your time. I mean, there may be reasons why you can't pick it up, but only when you pick it up, that's when it disappears from the memory. Okay, so now this is going to be our architecture, with realistic memory. So what are the complications now? What are the complications? When we replace the magic memory with this, you suddenly realize you can't do an instruction read like this. You have to initiate the instruction read. Only in the next cycle you will get the value back from the memory, right? So every instruction now is going to take at least 2 cycles because I initiate it and then I get the response back, from the memory. Same thing will happen if the instruction happens to be a memory access instruction. Then in the execute part, you will initiate it and then you will get the result back. So some instructions may take 3 cycles, some may take 1 cycle, some may take 2 cycles, etc. And let's see how does that come about. So this is my processor with realistic memory, right? So code to instantiate PC, RF, mem, and registers that hold the state of the partially executed instruction. And then you have the fetch rule. And what does the fetch rule do? It just initiates it, right? And it will put the right data into some intermediate stage, and you will go after that to the next stage, which is the execute stage. What will execute stage do? Anyone? You already know your 2-cycle processor, right? Princeton Architecture. So what will the execute stage do? Can it execute instruction in this cycle? It can execute all of them except for load and store instructions, right? So if the instruction is not load and store, then I just execute it and I will jump back to the fetch stage. On the other hand, if it's a load or store instruction, then I have to go into a new state. And let's just call it load wait state, at that point. Okay, so that's what you will see here in this thing, So first thing is execute all instructions except memory instructions and go to fetch. Or it's a memory instruction, so you initiate the memory response. If it's go to fetch for stores, but for loads you have to wait. So I'm calling that state load wait. I hope everybody understands. So I initiated an instruction fetch in the first rule. In the second rule, now I got the instruction. I execute it, I go back to the fetch rule, unless it's a memory instruction and unless it's a load instruction. If it's a load instruction, then I have to wait until the data comes back from the memory. Store, no data comes back, I can go back immediately to the fetch stage. So you do all this, right? And now you can see what will happen in the load wait state. You're going to execute the rule which says mem dot response, because you're waiting for the response to come back from the memory, and then you'll do various updates. And if you're wondering why I'm not showing you code here, because it's going to be part of the lab you're working on now. So believe me, by the time you do this lab, you would have designed a fairly realistic processor, which can use memories the way they really are in the system. I want to actually make it even more realistic. So you have already seen some operations which can't be performed in one cycle, not instructions. Even some ALU operations cannot be performed in one cycle. What would be an example of such an operation? Multiply, right? You have already done multiply, I think, in some lab. So you know that multiply takes some variable number of cycles. So now the question I'm asking from you is, can you actually integrate that multiplier into your design? Now suppose, this is not true, but suppose the multiplier takes 10 cycles. Should every instruction take 10 plus cycles? See, that'll be pretty dumb. We are smart designers, so we should spend that 10 cycles only if you happen to execute a multi-cycle operation, only if you happen to execute a multiply instruction. So now I'm going to draw, further distinction here. Fetch remains the same. In the execute part, I was first checking for, is it a non-memory instruction? Is it a memory instruction? And now I put in another case. Is it a multi-cycle ALU operation? If it's a multi-cycle ALU operation, then I know I'll need more time and I cannot go to fetch. And this is like fetch, execute, and after that sometimes you go back to fetch, sometimes you go to load wait, and sometimes you will go to multi-cycle wait. It's a multi-cycle instructions, and that is what is shown here. In this, if the state is load wait, this is just like before, and if the state is multi-cycle wait, because this operation is taking a long time, in fact, at this level of design, it doesn't look any different than the memory instruction. Memory instructions take a long time, multi-cycle instructions take a long time. It's just that the data is coming from different parts. In this, it will be coming from a multiplier or floating point unit, as opposed to from the memory of the system. So I believe we are not doing this one anymore in lab 6, but please understand it, because it's guaranteed you will need it for the project. Right? When you do the project, we want you to build very, very fast computers at that time. All right, clock speed. I said I'll say a word or two about clock speed here. This is very, very simple-minded analysis, but even the simple-minded analysis tells us something about how to think about clocks. So if you go back to the single cycle machine, or the way it was organized, then you had time to access the memory. This is where instruction fetch is happening, plus the time to decode, plus the time to do register fetches, plus the time to do the ALU operation, plus the time to fetch from the memory, right? And time to write back into the register. So if you look at these pieces, all these things are additive, and all these things have to happen in one clock cycle, and therefore the clock cycle has to be larger than the sum of all these things. But by separating memory, fetch part and the data memory into separate accesses, what I do is this time becomes, you have to do little less work. So it'll become, the clock has to be the maximum of either the data access part or the rest. But the rest never has memory access in it, except for instruction fetch part, right? Now, if you imagine that accessing memory is an expensive operation in terms of time, it has long latency, then what you will discover is that these two times are roughly the same. Certainly this time, this clock is faster than the first one. Because instead of 2 memory reads, it's doing only 1 memory read. That's good news. That means we can run it faster. Clock, in this design, in physical aspects of this design. But the problem now is when it comes to throughput, we haven't really won, right? You're doing fast stuff. Most instructions will get done quickly, but the memory instructions will take twice as long. So you say, oh, I will win with this new clock, provided the number of loads and stores is not larger than something. It's becoming a slightly more complex calculation. And as we do more sophisticated designs of the memory, these kinds of questions get harder and harder to answer. Exactly what is the clock speed? How long is the overall performance of the system? Because when we talk of clock speed and area, we are talking of physical properties of the circuit. But ultimately, performance question is not about that. Performance question is, how fast am I getting my work done? Which in this case means how many instructions am I getting done per cycle? And you made the clock faster, but you are taking more number of cycles to do every instruction, then maybe you win, maybe you don't win, right? So that's why these questions are very interesting. All right. So cycle counts are very, very important, but they're not the full story, but we'll be doing it all the time. From now on, anytime you do anything, we'll be counting the number of cycles it's taking to execute your program, and then we'll be analyzing it. And notice here, it's not as simple as saying you have n instructions, and therefore you will take m cycles. You have n instructions, then you'll say, well, tell me what fraction is memory instruction. Tell me what fraction is long latency, multi-cycle operations, etc. And this question will get more and more complex. How do we compute these things when we actually bring in the memory? So I still have 1 or 2 slides, so don't run away. Next time what we're going to do is look at the internals of the memory design. And just to set your mind, give you the right mindset, processor complexity is this much, and design of memory is not this much. Design of memory is also this much, right? So designing memories, internals of the memory, is extremely tough, extremely interesting, and if you have a very fast processor and lousy memory, you've made no progress. Because you have already seen in this simplistic calculation, memory access time will dominate, right? So this thing I don't have time to finish, which is what is this empty interface? And basically what happens is there is magic going on here. Obviously, if there was no way to do anything to this processor from outside, it would be like a black hole. But it's not a black hole. We cheat. So we say, okay, whatever program is in there will always start with instruction 0. We just declare that, right? This is to simplify our lives. And second thing we'll say is, we don't want to get into the vagaries of how to load the memory, how to initialize the memory, so it'll be preloaded. All the labs you will do in this class, memory will be preloaded with all the data, all the programs in it. And then when it finishes, it writes in some specific location in the memory. That's how you know you're done. Okay, so we'll be using all these ideas. All right, good. We'll continue with this. Next 2 lectures are on caches or internal design of memory. Very exciting stuff. Thank you.